To make the distinctions between these two types of Monte Carlo algorithms, we'll look at some probabilistic tools to talk about the kind of differences that come up when we try to boost the success probability there. And this is, I guess, depending on the flavor and the focus, is either called tail inequalities in the sense of the tails of a probability distribution or random variable, or concentration bounds. But let's take a step back. So the key question, or the key problem is, with randomized algorithms, the running time is a random variable. Now, as always in algorithms, you'd like to know for two algorithms which one is better. And that's always been a tricky question already with asymptotics and so on. But here is, even for a single input, it's not so clear. It can always happen that one algorithm is faster than the other because it's random. So how should we compare these? There's a direct way. If you just take the random variables for one algorithm, the time on a specific input, right? This is the easiest possible case. You have a fixed input, and then they both do something random and then take their time. One simple option is called stochastic dominance, where you directly compare two random variables. And the definition is just, say it's a real valued random variable. For all possible values, the probability that this one variable is above that value has to be bigger than the probability for the other random variable. Then we would say that this stochastically dominates this one. I put weakly here. The definition in books usually includes this for all t, and there's one t where the probability is strictly greater. But I don't care so much here. The point is, this is actually a very stringent requirement. The graphic you should have in mind is to draw the cumulative density function, the cumulative probability function. So you have f of x, and here are the possible values of x. Let's make this bigger. So I'm comparing, let's say this is x, maybe that's let's still call it x and y. Nicer to write. So cumulative probability function is just what's the probability for capital X to be smaller than a certain value, right? So this is this value x. And so this is going to be some increasing function, right? Maybe for x it looks like this, it plateaus a bit like that. And then we have our variable y on the same space. And now what the dominance means at any point, right? If I look at some point x, the probability that y is bigger than that point has to be, say we want x is, let me write this as this, it's larger than y. Then at any point, the probability that x is larger than this point should be bigger than the probability that x is greater, as it says here. For the cumulative density function, we have to take the inverse probabilities. And so 1 minus f of x is greater or equal 1 minus f of y. That's what this translates to. And then, of course, it means f of x is less or equal f of y at any point x. I should have not written this like that. The random variable should go in the subscript or something like that. And that's the y. Oh dear. Let's call this t. And here we should have y of t. They're on the same axis, and I didn't draw y yet. So it might be the same for a while, then maybe it trails. And then it's maybe like this. They both have to end up at 1, I guess. So at every point it's below, which what I drew here is exactly not like that. Okay, maybe like this. Okay, sorry for the messy write-up. Let me just write it like this. Okay, so it's a simple concept, but if you think about it, this is actually very unlikely to happen. I mean, if that's true, then we would certainly want the algorithm that's at each point more likely to be faster than that point than the other. But we can't actually expect this for algorithms to happen. Most of the time, the world is not so simple that one algorithm is strictly worse than the other. Yep. Sorry. Yep.
So Fy is always greater than Fx?
Did I draw it the other way around somehow? So this is the probability that x is greater than some value t. If I include the t here, then that matches, right? Then putting x on this side, y on this side, we get fx of t is less than fy of t, which is certainly not what I was drawing. So the formula was right, but the picture was wrong. So maybe it jumps to a higher value straight away, and then maybe it looks like this. Yeah, good catch. Yeah. Of course, I was just checking if you pay attention, as always. The point is that this is hardly ever true. So if you can do this, it's nice. It can be useful for other purposes sometimes, but we'll not get into this here. The other option we have is, well, what else do we know about random variables? We can take expected values and hope that that's gonna be well defined. That also has the benefit that you can compare the running time of some random variable against some absolute threshold. Say you have proven some general lower bound that holds for all thinkable algorithms. How close does your algorithm get to that lower bound? Well, with stochastic dominance, it's hard to answer that question. With expected values, you can at least compare the two numbers, but it has to be taken with a grain of salt because, of course, expectation is only the typical value. The problem there is if you just look at expected values, as all the data scientists know, it's not always representative. Just to make a tiny example, suppose you have two algorithms, both with expected time 2, but one takes in half the cases 1 time step, and the other half cases 3 time steps, whereas B is much more unbiased. 99% it's fast, but then there's this completely destroying outlier. Now, it's actually an interesting question which of the two you would want to use in practice. But certainly the expected value being the same is kind of annoying because we can't even distinguish that they are doing different things. And I guess the second algorithm is not so great because it'll always be slow in the time when you use it, where you require some quick answer. So we probably prefer algorithm A, but expectation certainly doesn't tell us. So one option is to look more closely, and we'll do that. But the algorithmic solution actually is try to make an algorithm where this doesn't happen, right? This is a flaw in algorithm B. So we'll try to make it so that the actual time an algorithm takes is rarely far away from its expected value. That has two benefits. We can deal with the expected value and compare single numbers, which makes life easier. But also a robust performance is anyways desirable. Formally, what we'll do is this concentration bounds. We'll try to say that a random variable is not too far from its expected value. That's what this chapter is about. And then if we can achieve that, we're happy both from the practical side and from the theoretical side. So let's have some tools for this. First of all, some terminology. And so the caveat is that this term with high probability, as vague as it sounds, I'm using it here in a very technical and formal sense. It means a very precise thing, which we'll get to in a second. It's used very much in the literature because I'll show you why, but not always the definition is exactly the same. So you have to be a little careful. Maybe you can call this with very high probability. I've rarely seen a stricter notion. Okay. All of this has to do with asymptotics. So it's always assuming that there's some dependence on a variable n that goes to infinity, input sizes. An event happens with high probability when the probability for that event is 1 minus a small error term, but really it has to be very small, namely super polynomially small. One way to write this is to say for every constant c, every degree of the polynomial for the error term you give me, still you can show this asymptotic. Okay, so it's a strong requirement. That's for events. The slightly more widespread version or more useful one is to bound random variables. And this is a tad more subtle. So we say a random variable, again assuming it depends on some parameter, is in O of f of n with high probability. So the whole phrase, this whole thing is one technical statement, okay? Well, when this is true, well, what does it mean? Again, with high probability, you should have some error probability that's super polynomial. But now the constant in the big O, right? There's a hidden constant in front of f. That's the d. That is allowed to depend on your exponent. This may sound a bit arbitrary, but this turns out to be the right definition in many cases. This is often what you can show, and it's sufficient when you can show it. I think it's also justified to say that this is really with very high probability. So intuitively, it feels like if the probability goes down super polynomially, that's going to be a safe bet. And you'll soon reach the point that it's more likely that some quantum physics behavior breaks down than that the algorithm is incorrect, if n is large. Questions or clear so far? It's a very strong notion, as I said, and the reason why we pick this specific and very strong notion is this simple lemma. If you have some, say the event is that our algorithm A does not fail, then I can repeat my algorithm a polynomial number of times. If I make these independent repetitions, that's important, independent repetitions of that event, still not a single of them fails, again with high probability. So it's a very robust notion. If you can prove this, you basically can iterate things a polynomial number of times without seeing a change at the level of this definition. And so let's briefly prove this just to see why this is true. And let me take the definition with us. Okay, of course it will jump away as soon as I click to the next part. Well, C is the constant from the definition. So we have to show the claim again. If you look up, we're trying to show independent repetitions n to the d, independent repetitions of A are such that not a single of them fails. That's a new event. The new event is the union of all those previous failure events. Okay? The ith version of the event fails. That's our event AI. And then the event we're now looking at is that any of them fails. That's the event we're studying, and we're trying to show that B happens with high probability. Sorry, not B. We're trying to show the negation happens with high probability, so none of the AIs fail. Okay. So C is given from the definition. We have to show this for any exponent. Of course, consistency in notation. Imagine I would have written Fi here for fail. Fi is the event that the ith run fails. Now, this happens with high probability by definition, so we can pick an arbitrarily big exponent in the error probability. And I mean, it said in the lemma that the algorithm does not fail with high probability, so that means the converse event has this small probability at most. Then we write the union of all those events. That's the probability that any number of them fails, but not none. Now, by the union bound, right, this is the events are not, well, I guess here they are independent, but we don't want to get into the question of how many fail. We just use the union bound, and I guess here it's an equal because they're independent, but it's good enough to upper bound it. So we sum up the probability that each of the events fails, and that by assumption is this is bounded by this, and we have n of d to n to the d of those. So if you multiply that out, of course, you get the n to the minus c that we wanted to show. Okay? So with high probability, if we can show this, then that an algorithm does not fail with high probability, you can repeat it a lot of times. And we'll also use this to combine other things. It's a very robust notion. That's why we make it so strict. And you can work out the details. If you don't require roughly this definition, these kind of repetitions wouldn't be allowed. All right. Time to get into business with actual inequalities to bound probabilities like this. And the first one is Markov's inequality, which you may or may not have seen, but it's cute enough. It's a very simple thing too. All we know, I wish I had that in red. We need a random variable that's positive or non-negative and real valued. Okay, it's emphasized here. Then we can say the probability that this random variable exceeds a certain number can be bounded in terms of its expectation in that number. Okay? Let me prove it first, and then we'll come to what it means. The proof is really kind of cute. So we have this a given, and it's greater 0. And then we define some event or indicator random variable. That's this indicator of x being greater than a. So it's a 0, 1 event. That is, you could also write it as x being greater or equal 1 with Iverson bracket, same as saying it's 1 if this is true and else other 0. Okay, so I claim that I is less than x divided by a. And for this, you have to take the two possibilities, right? If x is indeed greater than a, then I is 1. But then x is greater than a, so x divided by a is greater than 1, and the inequality is true. The other option is if x is strictly less than a, then I is 0, and well, x is non-negative, so it's not going to be negative. So in both cases, this is true, okay? No matter what values x takes, this is always true in terms of the actual random variables. Clear? Now let's take this inequality and take expected values on both sides. So what we get is the expected value of I is less or equal the expected value of x divided a. And so we're getting closer to this. Let me write the inequality the other way around. I think this is convenient here. I've already used linearity of expectation because a is a constant. I can pull the expectation up to only cover x, right? Sorry. That's the expectation of I. And because this is an indicator random variable, I mean, the expectation is the sum of 1 times this probability plus 0 times this. So that's exactly the probability that x is greater or equal a. And that's it, right? That's the statement. So the proof is almost boring. But the inequality turns out to be tight in the general case. That's the best you can say if you want to relate x or bounds for x to be large to its expected value. A good thing to memorize is maybe the statement below here. So you just reformulate the inequality a bit. I think this is slightly more intuitive in the following sense. We expect that x is roughly half the time larger and smaller than its expected value. So here the question is, if it has to be a times larger than its expected value, how likely is that? And Markov's inequality says, well, at most 1 over a probability for that. So keep that in mind. Before we move on, I want to give a brief visualization of this inequality because I think it's good to stick in mind, which only works for natural numbers, but oftentimes we have that anyways. So the thing about natural numbers, if x is a random variable over n0, is that we can rewrite the expected value in a nice way. Probably you've seen this before. That's just the definition. Sum over all possible values times their probability. But then if you group this, I'd say x takes values 1, 2, 3, 4 with certain probabilities. Then what this first sum does is sum this up times 1, times 2, times 3, times 4. So you're basically doing this, and then you have 2 times this small thing, 3 times the large guy, and 4 times the little one. That's your expected value, right? And another way to write that is if you look at this sum, it gives you the same terms. Is that the right way around? I'm confused by my picture. Yeah, I think the way to group it is to say, previously this came from 1, but you could say the 1 is summed up. The 1 gets 1 contribution from each, then the 2 gets 1 here, and the 3 only gets these, and the 4 only gets the last. Right, so the probability that x is greater or equal 1, that's comprised of this part and this part and this part and this part. And I'm starting with 0. That's the mistake. So you could rewrite this as one large pole where you have probability for 1, then the probability for being value 2, the probability for value, sorry, the probability for 2 was the small one, then this one, maybe like this. That's greater or equal 0. The probability for greater or equal 2 is just this little guy, then these guys, this, and so on. So what's missing here is exactly probability for x being 1. And so on. Okay, a bit more careful here. And then we have the last bit, greater or equal 4. Now, what is Markov's inequality doing? It takes the, if you draw this in the more general case, you would draw the probability that x is greater or equal a and plot that over a. Now, this is the inverse of the cumulative density function or cumulative probability function. So this will be something that goes down. In our example, maybe like this. There's a bigger step down here. And then, okay, one more step and then 0. Okay. If you pick any position for a, then the probability that x is greater a is this point. And so you can take this rectangle has area probability x greater or equal a times a. And the whole region below the curve here, this entire thing, that's exactly the expected value. Right, that's from summing up from this sum, you sum up for each value the probability that it's larger than a. And so, of course, the red area lies below the curve, and so must be a subset of this one. So you get that this one has to be less or equal e of x. That's another way to get Markov's inequality, right? If you divide by a now. All right, maybe it's not that useful. Maybe this picture is worth keeping in mind, but you have to remind yourself what is on the y-axis. Okay, good. So as I said, there's examples of random variables that you can construct where Markov's inequality is, in a sense, the best you can show. But it's not actually such a strong result. if you apply it to some, you'll do it in the exercises, you don't get as much from it. And so it seems like a weak bound, but it's a general result because it doesn't restrict the random variable that you put in much. So most of the time when you use it, you're not using it on the original, say, random variable of interest, like the running time of your algorithm, but you apply some function on this random variable. As long as it keeps it positive, you can apply Markov's inequality to that mapped random variable. And that's actually much more powerful. So the first version of this applies it to essentially the difference from its expected value. For that, we should define moments of random variables briefly. Given a random variable, a moment of the random variable, the kth moment is just the kth power, and then taking expectations. So also, it means the expected value is just the first moment. Sometimes people call it like that. There's two flavors. The kth moment in this case is the pure moment, just taking powers. Often more convenient is to take the centered moment and also take absolute values. So you take x, you subtract the expected value so that the result has expected value 0 now. But then you raise it to the kth power. So what this does is kind of, well, the centering means expected value is 0, but then you're also taking powers, which means you make the variable more extreme. If it was close to 0 before, it's much, much closer to 0 now. If it was far away from 0, it's much further away from 0 now, depending on whether it's larger or smaller than 1. We'll see the effect of this in a second. You'll be familiar with the second-centered moment. That's just the variance. And sometimes people use standard deviation because it's a bit more intuitive. That's just the square root of the variance. And of course, you can do similar things with the higher moments if you want. Now, one thing to take care of is these are expected values of some random variables. We may not have convergence. In general, these are infinite sums or integrals, and they may not exist. So you shouldn't assume that, but oftentimes you can just calculate them and then you know. The first usage of these moments and Markov's inequality is called Chebyshev's inequality. More and more Russian names. The statement gives you a similar flavor as before for Markov. You have some notion of x being far away from its expectation. Here it's two-sided in the sense that you take the absolute value of the difference. Markov was just being above a threshold. Here it's being by a factor away from the expectation. And now the upper bound is involving the variance, but also you should notice that there's an a squared. Previously, Markov, it was x greater or equal a is expected value over a. Now we get an a squared, which means for large a, this bound is going to be much smaller. Okay, I mean, lying away that the variance is there, but oftentimes the variance is not much, much bigger than the expectation. Let's also prove this is actually very simple. I'm almost tempted to leave it at that statement, but maybe it's worth doing it once. Oh, we can use normal parentheses. We just define a new random variable. Because of the square, it's for sure non-negative. And then I'm applying Markov's inequality to this guy. So Markov's inequality, again, says the probability that this is greater or equal a is less or equal than the expected value of this divided by a. Now, let's just pick this apart. So what's the probability that this is greater or equal a? Let me call this b here just in anticipation of a change of variables. If I plug in the definition, that's almost what we want, but there's a square. So if I take, this is an inequality. If I take a monotonic function on both sides, it doesn't change the inequality or the validity. So I'm taking square roots on both sides. And we'll call this A, obviously. And then I'm just going to plug in what we have here. And we'll use that the expected value of this guy, it's the definition of the variance. If you forgot, it's right here. So that's nothing but the definition of the variance of x. And here we still have b. But if a is the root of b, then that's the same as a squared. Okay. So here we're using Markov's inequality. And so see what we've done. We've taken a random variable, and I'm implicitly assuming, I mean, the bound makes no statement if the variance is infinite. Let's assume the variance is well-defined and converges, and the expectation then too. So if I have a random variable with slightly more assumptions, namely that its expectation and variance exist, I can turn that into a more centered variable, or a more extreme variable, say, by centering and squaring. And if I then apply Markov's inequality, I get a stronger result, just because this is a more extreme random variable that I'm applying the bound to. Okay.
Where does the square come from?
We're taking, so from in this step here, take square root on both sides. And so b turns into square root b, and I'm just relabeling that as a, the change of variables.
Of Markov method, should it be just a? The branch?
Here? Well, it was a b, right? We're applying Markov's inequality to the original thing. So maybe I should have left it and then said, the thing we apply it to is the random variable y being greater than some arbitrary constant b. And then that's the expectation. So let me leave here the expectation of y divided b. That's what Markov gives us literally. And then I'm plugging in the definition of variance and the definition of a, if you want. It's basically just a calculation. The key thing is this first line only. What we get from this, apart from obviously the inequality as stated, I think slightly more intuitive is the following. If you have a sequence of random variables, so they depend on n, where expectation and variance exist, and the crucial additional property here is that the standard deviation or square root of the variance is little o of the expectation. And I think this is a very intuitive statement, because that's how standard deviation is used in statistics. You look for a random variable around its expectation, and then to left and right, a certain multiple of the standard deviation. That's where you expect the random variable to land. Now, in parentheses, if everything is normal and so on. But here, at least something can be said in this under this assumption. If the standard deviation compared to the expectation goes down, becomes smaller, then these random variables converge in probability to their expected value. More formally written, the ratio goes to 1. And convergence in probability is just the definition of this guy. For any epsilon that you pick, any fixed epsilon, the probability that you're further away than epsilon from this limit point converges to 0. The probability converges to 0. It's not the strongest notion of stochastic convergence, but let's not get into that too much. At least Chebyshev's inequality is strong enough to show that if you have standard deviation smaller than the variance asymptotically, the things will get very, very centered. You'll get closer and closer to the expected value as bigger the bigger n gets. All right. So this looks promising. We're getting closer to replacing a random thing by its expectation and getting away with it. But this is still not quite this strong notion of high probability. If you stop here and try to get this, it doesn't work. And if all you know about your algorithm is expectation and variance or standard deviation, again, this is kind of the best you can do. So you're out of luck. You have to make stronger assumptions. So the third and final point of this journey is to think about scenarios where you can make a much stronger statement. And so we'll come from the other end. So far, we've kept things as general as possible and saw how good a statement we can get out. Now let's go the other extreme. Pick a very specific scenario, but at least one where we know we get the sufficient results that we want. And intuitively, what we look at is a random variable x that's made up from a sum of many small parts. And these are all bounded in how much they contribute, and they're independent. So the larger you make n, the more the randomness has to average away, because there's independent random bits, but each contributes just a tiny little additional factor. And so maybe intuitively you'll expect something like a central limit theorem type of convergence. So I don't know how much the vagueness helps you here. We'll see concretely what this means in these bounds. That's the most general version that we'll use, and it's usually good enough for most algorithms. You could push this further, but I'm not going to do it here. And we'll make a simpler statement on the next slide. The setup is you have indicator random variables, so just 0, 1 random variables. So they're Bernoulli trials. They're mutually independent. That's the crucial bit. But the generality we allow ourselves is that the success probability may be different for the different xi. Okay. Then the thing that we're interested in is their sum, and we keep summing more and more of those little parts. Then you can write the expected value of x. So that's denoted by mu here. It's really just the expectation of x. By linearity, that's the sum of all those pi. And then you can prove these inequalities. The probability that x is a 1 plus delta fraction larger than its expected value is some more or less ugly constant depending on delta. But say you put delta to 1, right? Then what will we get? This is e, and we divide by 2 squared, so e over 4. The important point is this is less than 3 over 4. Okay, it's less than 1, and a good bit away from 1 actually. E is also strictly less than 3. So you have some constant on the left that you take to the power of the expectation. And the expectation here is growing because you add more and more of those variables. I mean, the expectation is effectively linear in n if the pi are constant. If, say, the pi are all 1/2, then n/2 is the expectation. So the probability that you exceed your expectation by a factor 2 goes down like an exponential function, 3/4 to the n, or n/2, right? So it's a very, very strong concentration because you have an exponential bound on the probability. And you can prove a weaker version for a specific delta where just the right-hand side is a bit more convenient to work with. So the second equation follows from the first. That's just if you make the assumption that delta is less than 1, then you can bound things in that way. That's not so interesting. What I want to give you the proof for is the first part, because it shows exactly why this kind of result is possible. Now, it gets a bit more arithmetic in a way, but I think it's worth suffering through this once just to grasp where this is coming from so that you can generalize it if you ever need to. Maybe before we do the proof, let me show the simple version that we'll mostly use. This is just the special case of the previous statement where we say all the xi have success probability 1/2. You're summing up independent identical Bernoulli trials. That's called the binomial distribution. As in particular, you have n independent coin flips, each succeeds with probability p, and you take the sum, how many came up with heads, say. That's your random variable x, and then you can essentially plug in what you have from the previous bound. What I've done here is combine the two. You take n minus this to get a bound that is two-sided again. So you take x, you divide it by n to kind of remove the scaling, because x would grow with n. You take x divided by n and subtract p, which is the expected value. So the probability that this difference from the expectation is larger than some constant delta is bounded by an exponential function, and you even are allowed to square the delta in there. But this is x with e to the minus something squared, so this is really, really small. Okay. In particular, you can use this to show that in our sense, with high probability, we're finally there. A binomial random variable is in this interval expected value plus minus a tiny bit more than square root n. Okay. That's where we want to get to. And we'll then apply this theorem to some algorithms. Maybe tomorrow or just the end of it today. We'll see. I do want to give the proof here. So we're again applying Markov's inequality. But we have to pick a variable that's even more extreme. What we had before was take x minus the expected value and then take a power squared. What's more extreme than taking polynomials, exponentials? So it's a bit more tricky this time. First, we need a parameter. So what we'll do is it will show a general bound depending on this parameter t. And then you can, at the end, pick the best t to get the actual inequalities that we claim. Then we apply our Markov inequality to the following random variable. e to the t times x. So we take our sum of independent things, we multiply it by t, and that's the exponent. So far, this is essentially just falling from the sky, but that's where you apply Markov's inequality to. It's not exactly following the straight schema. So let's start from the beginning. We want this part, x, to be 1 plus delta greater than its expected value. That probability we want to upper bound. Now I'm using this transformation in here on both sides. I'm applying the function e to the t times the thing that's there. So I get the y on this side. And on the right-hand side, I get this lovely expression e to the t times delta 1 plus delta times mu. Okay, let's see what we can make of that. Let me stress here that this exponential is always greater than 0, so we can apply Markov's inequality to that guy. To do that, though, we have to rewrite it somehow, right? Markov's inequality you have to be greater than, so you have to know the expectation of y. So, and then we divide by this friendly thing. What's the expected value of y? Well, we just plug it in and see what happens. We're going to carry around this factor in front for quite a while. So I'm going to take a pause here and just evaluate what the expected value of y is. Of course, just by definition, it's this thing. And what was x? X, the sum of all those independent Bernoullis, okay? Now, here comes the trick. That's an exponential function. We have a sum in the exponent that turns into a product. So the e to the t is in front, and then we have the product of e to the xi. You can also leave the t inside. This turns out that's convenient. Let's leave this inside. Pull it into the sum. And now again, a crucial step. These xi are independent random variables by assumption. And e to the t xi as a random variable. So if you say yi is this guy, these are also then independent. Because the xi's are. And what have we learned about the probability, the expected values of independent random variables? They factor. So in particular, the expected value of the product is the product of the expected values. And of course, this is the step that you would not have been able to do without this strict setup. Right? This is Chebyshev's inequality can never get to this, so you're forever stuck at kind of on this left side, or I don't know. Okay, then the expected value of these guys, xi is 0 or 1. So let's do another side calculation of the side calculation. Xi can be 0 or 1, so that's easy. If it's 0, then e to the t times 0 becomes e to the 0, that's 1. And if I plug in 1, then I get e to the t. And of course, we know what these are by definition. Again, you know, these are Bernoulli pi. So it's 1 times 1 minus pi plus e to the t times pi. Because here the 1 can get rid of. So that's this expected value that we're now going to plug in up here. Okay, let's do that. So e of y is equal to this lovely product. And so we can slightly rewrite this as 1, this guy, and then plus pi times e to the t minus 1. That's just rewriting this bit. And now we have to use a little trick. We're basically using the inequality 1 plus y is less or equal e to the y, which you could either look up on the TCS cheat sheet, or you remember that any convex function lies above all its tangents. I guess that's essentially the definition of convexity, but the prototypical example of a convex function is e to the x. So that's a convex function. It bends upwards, and if you look from below, you never see concavities, I guess. Well, and you can pick at any point. You can pick a tangent, and the function will lie above it. Okay. And this 1 plus y, well, that's exactly the tangent at 0. Let me just let me move my y-axis, then it's the right one. If you plug in 0, then you get the value 1. That's where you start. And if you take the derivative, that's the slope of the tangent at this point. The derivative of e to the y is e to the y. Plug in 0, you get tangent 1. So 1 plus 1 times y is the line that you get there. And so, of course, 1 plus y has to be less than e to the y. That's if you don't want to learn formulas by heart, then this thing, right, by the formula is less than e to the whatever we have here, pi e to the t minus 1. And then you have a product of these. Is a product of e to the something. Let's pull out the exponential function. And then you have the sum of these guys. Okay. Now one more step. We can pull out this common factor from the sum. let's do a slow-mo. So it's e to the t minus 1. And then the sum. But the sum of the pi, we know what that is. That's got a name. That's exactly mu, because that's the expected value of x. Okay, so now we're at the point we've computed e of y, or an upper bound for it. Let's continue the original equation for where we started. The probability that x is greater or equal 1 plus delta times mu, which was this guy. And it ended with expectation of y divided something. That's where we're continuing. All right? So make a bit more space maybe. The probability that x is greater or equal 1 plus delta mu was less or equal e to the y divided this lovely term e to the t 1 plus delta mu. Now we plug in this part. And we get e to the mu e to the t minus 1 divided e to the mu t 1 plus delta. And so the last bit is you have an exponent at the top, an exponent at the bottom, and there's a common e to the mu, so you pull this out. Yeah, I guess you could do this already at this step. Why doesn't e to the mu simply cancel? Because it's a minus. Sorry, you cannot pull it out at this point. Yeah, I confused myself. It's e to the this minus this. So you can't pull it out yet. I guess that's the end of what you can do for general t. So far, this worked. The whole derivation is true for all possible values of this parameter. So you can plug in any value that satisfies this, and you get some specific bound. And one convenient choice, because we have this e to the t term that's really annoying. We plug in something that gets rid of that and relates that to delta. And this is kind of something people found out by trial and error. So you plug in here, continue the equation, right, kind of equal. Then it's e to the mu. E to the t turns into this log. Turns into the 1 plus delta. And we have the minus 1. And here we keep the log 1 plus delta moves into the basis of this whole thing. We're using e to the log of the thing. And what's left is mu and 1 plus delta. Okay. And now you pull out the mu. I guess I could have done this up here. Yeah, you could have written it like that. So because that's the whole thing. It's e to the t minus 1 to the mu, e to the t 1 plus delta to the mu, and then pull it out, but okay. The 1 cancels, right? It's just e to the delta divided this longer term 1 plus delta to the 1 plus delta, the whole thing to the power mu. Okay, that's finally what we wanted to prove. Okay. Is a bit heavier on the calculation side, admittedly. The thing is, you don't have to ever do this again unless you run into an application where the given theorems aren't general enough. But let's recap the key trick. The key trick was, again, to use Markov's inequality, but to a variable that's much more extreme if x is extreme away from 0, then this is even much further away from 0. And because we could factor the random variable by taking the sum into the exponent, you get a product that you can then factor because of independence. That's what makes this this statement tick. And the rest is a bit of rote calculation. We'll actually mostly try to use this version just because it's much cleaner, and many times the random variable we're bounding comes from repeated applications of something, so we can assure that it has this binomial form.